Hello，有了，好，OK。喂喂，杨姐有点问题。Hello，在，喂，这样可以了吗？好，干扰，对。We have two machines on at the same time, so the one in the drawer, another receiver was on, so I turned it off. Now everything is okay. Okay, right. So welcome back to DSP, and we are going to meet 2 hours, maybe less than 2 hours. I say, let's plan to leave like by 6 o'clock, maybe 6:10. Okay, no more than 6:10 because we're doing this for a few reasons. Because one is the main reason is because last Thursday we didn't have a class meeting, right? So it was like the day before spring break. So technically, it wasn't a spring break. It's called 弹性上课. Anyway, so the university officially requires us to find another hour to compensate for the missing hour we lost last week. So I think today, after midterm exam, we can cover some new materials. So let's take it easy. All right. So today we will shift to the next topic is filter design, to design something. So design versus analysis, okay, to design, to analyze. So previously, we've been studying this system, yn, which can be calculated iteratively by looking at past samples, like this, ak, y, the kth sample in the past. So k could be from 1 to, let's say, finitely many m samples, and form a linear combination like this. And then we also use the input. Again, x being the input, y being the output. So we also look at input signals, x. So that's sort of the framework. We've been studying how to analyze the behavior, and there's a minus sign by convention, 习惯上啊. Been trying to study the behavior of such kind of difference equations. So we know how to, for example, calculate the impulse response. We learn how to map everything, the equation, to the z domain using z transform. We know how to form a system function h of z that's defined by yz over xz. You will very soon realize that this formulation results in an expression of bz divided by az, where b and a are both polynomials, right? So such kind of formulation we have studied from until last week. So these are our effort so far has been how to analyze the equation, how to analyze the impulse or calculate the impulse response, how to analyze whether or not the system is stable in the BIBO sense by looking at what? The roots of A of z, right? If everything is inside the unit circle, we say things are fine. The impulse response is going to converge to 0. It's going to be a stable system. Otherwise, it's going to be unstable, things like that. So all that sort of things are about analysis. Given an equation, given the system, you know how to predict the behavior. That's analysis, 就是做分析啊. But now, in the rest of the semester, we will try to learn how to learn a different mindset, 不同的心态, different mindset. This new mindset is to design. Now, if design is sort of the opposite of to analyze, to design is the opposite to versus to analyze. They are opposite. When we design something, you are given some expectation. 期待的啊。You've given some expectation. Your system is expected to achieve certain performance. There's an expectation, and then you need to figure out an equation like that. Figure out this equation. Figure out all coefficient A and B, and as well as the order. That's also important. Figure out these parameters, M, N, and all the coefficients, such that your system as an equation, such that the resulting equation satisfies certain specification. That's a mindset of designing a filter. Okay? For example, design a filter, find these coefficients, find these parameters so that your system is a good low-pass filter. So that this equation gives you a low-pass filter. So that's the mindset, okay? So just by the way, repeatedly, we will discuss low-pass filter a lot as the most simple example. And so here I prepare 3 lectures on this very topic, filter design, 3 lectures in a row, 7, 8, and 9. And so today I would like to first give an overview what kind of methods are there. So very soon, so let's start. Okay, so filters can be separated into 2 different kinds, 2 different categories. And each of them has their advantages. Okay? The first kind of filter is called IIR, or infinite impulse response, meaning that the impulse response lasts indefinitely, 就是无穷长 or indefinitely, infinite impulse response. Versus the other kind is, of course, infinite versus finite. Okay, infinite versus finite, the opposite. So the second kind is in a sense, easier, called FIR, right? The kind of filters with impulse responses that are finite length in time. Okay, finite impulse response, infinite impulse response, IIR, FIR, 2 different kinds. Okay, and their design requires very different way of thinking. Okay, very different way of thinking. First of all, the first point is about implementation. IIR is implemented by LCCD, the linear constant coefficient difference equations, by this equation. IIR is implemented by this equation particularly with the feedback right here, with feedback terms right here. Those are IIR, implemented by basically difference equations. Whereas FIR is implemented by convolution, and convolution turns out can be accelerated. In other words, we can reduce the computation load through fast Fourier transform. Okay, something to keep in mind. Implementation is quite different. IIR is direct implementation using this equation. Okay, but FIR can be accelerated by FFT, by fast Fourier transform. And how about their advantages? The advantage of IIR, to conclude, it usually has a smaller computation load than FIR if they are given the same specification, or I mean, when we say specification, that means expectation, performance expectation, called specification or spec. Usually, IIR is computationally more efficient than FIR if when we want to reach the same specification, such as low-pass filtering and so on. But then, the drawback of IIR, there's one drawback that I want to mention, which is about group delay. Okay, and group delay is not constant, which causes what we call dispersion. Dispersion 就是像叫中文 in Chinese 叫色散啊 dispersion. IR inevitably has dispersion. That means different frequencies has different latency, delay. Different frequencies are delayed differently. 1 kilohertz faster, 2 kilohertz slower, and that's called dispersion. Dispersion, which is not good. Okay, generally we want, this is a drawback, 是一个缺点 for IIR, to summarize. Whereas in FRR, systematically they can be designed to have linear phase response. Linear phase response meaning constant group delay. Every frequency passes through the system with an equal delay. Okay? All delays are equal, but some are more equal. All animals are equal, but some are more equal. Animal farm. 所有动物都平等。最近 yeah, it's been on the news. Anyway, so FIR has an advantage that every frequency has the same group delay. In other words, the phase spectrum is a straight line, linear phase, and that's an advantage. We shall also cover like the design to design IIR. So we will cover that. We'll start covering that later today. Start with IIR. FIR will be lecture 8 and 9. Lecture 7 is about IIR, right? So lecture 8 and 9 will be about two different methods. One is called the window method, the other is called the optimal method. So we'll cover that. And so that's kind of a one-page overview. So this is a note that I created by myself. So after studying all the three lectures from 7, 8 to 9, I recommend you can refer back to this page, okay, to see if you understand all the concepts, the reason why the advantage and why there's this drawback versus FIR. Constantly, please come back to this page to check your understanding, okay? It's a nice summary. Okay, so now a bit of a preview of how we design an IIR filter, okay? And this is quite counterintuitive, should I say? 有点违反直觉. Counterintuitive in what sense? So remember that this course is about digital signal processing, right? But in designing a digital IIR filter, we will borrow from analog. That's the counterintuitive part. We're about digital processing, but now to design a digital filter for sure, we start from analog. And that is what I think is counterintuitive. 有点违反直觉, a bit counterintuitive. We will borrow an analog prototype using some kind of technique called bilinear transformation. Analog prototype. You know what is a prototype? What is a prototype? Prototype is prototype. Does anybody know the prototype? 刻板印象, stereotype. Good. How do we translate prototype? What is a prototype? 原型啦,原型. Prototype. It's a kind of a model or a product that you quickly develop first to show your idea, to demonstrate your idea. That's called a prototype, business-wise. When you develop a product, but you don't have the factory for now, so you just 3D print your prototype and show it to others to seek opinions. So we here in this context, we borrow from an analog prototype. So we start with a well-known analog system by the name Butterworth filter. So an analog system, a circuit, really. If you think about that. So from there, then that analog prototype will have a system function in the Laplace domain. So here on the left, we have the S-plane. On the right, we have the Z-plane. Okay? S being Laplace transform variable, right? Laplace transform. So you can describe any linear, time invariant, continuous time system, analog system using Laplace transform, right? Using system function in the S domain. So here, that analog prototype will have a system function in the S domain. And then let's say if we start with some kind of h of s equals to, just interestingly, it can be also written as a constant, perhaps, divided by a polynomial, let's call it a polynomial of s, right? maybe Sn plus an minus 1, Sn minus 1. It's also a polynomial of S, yeah. Maybe, yeah. So we'll be using this prototype in the S domain. A1S plus A0, okay? And the analog prototype may have some nice properties. So we'll see a moment. Yeah. And then we are going to turn this analog system into a digital system function. Okay. From here, let's say if this is analog, yeah, we want to somehow perform a bilinear transformation, something called bilinear transformation, by defining now h of z equals h of a, but now replace S with a mapping function. Yeah. Okay. Just replace S with a mapping from Z to S. The resulting function now becomes a function of Z. So that's the counterintuitive, the kind of the core technique in designing IR filter. Begin with an analog, a nice function in the analog domain, and then turn it into some h of z. And from here, then you'll soon realize that yeah, h of z, then just no surprise, can be written as bz divided by a of z. Then from there, you can go back to an LCCDE. Yeah? Okay? It becomes something that can be implemented in this form. Okay? So that's that kind of a few steps. Prototype, bilinear transformation, then back to difference equation. That's the 3 steps, okay, in designing IRR. So this is the mapping I'm talking about. So here, it turns out that bilinear transformation has a very nice property in that it maps the left-hand side, the left half plane. Anything on the left of the imaginary axis of the S-plane, it maps this entire region to the inside of the unit circle. And it is a nice property. We'll explain why, okay? So mapping from complex plane to another complex plane, from S to Z or the opposite, is, yeah, you can go either direction, from here to here, or from there back to here, yeah. So bilinear transformation will be the key trick. And so here is another look, okay? Suppose that now, when we have an analog prototype and we want to evaluate its frequency response, and that can be simply done by evaluating this system on the imaginary axis. Just substitute S equals to J big omega. That gives you a frequency response, right? So for example, if we have a prototype that looks like, which has this frequency response, pass band, maybe some stop band with ripples, yeah? That makes sense? Can you look sideways, okay? You need to just look sideways. So this is an analog prototype of a low pass filter with pass band and stop band, right? But then, bilinear transformation gives you this. Now, if you take a look, here, the frequency axis is big omega. Whereas right here, that's small omega, okay? So this frequency response, actually, after bilinear transformation, the frequency axis is compressed. It's compressed to within this interval, 0 to pi, okay? And that's very nice. By doing so, we convert an analog low-pass filter to a digital low-pass filter through this frequency compression, okay? Actually, there is an exact expression here. I'm not sure if you can look from the back of the classroom. So there is a relation between big omega and small omega, okay? And this relation, of course, we were compressing the entire infinite interval from 0 to infinity, because analog frequency can go from DC to infinity, right? So the entire frequency range somehow we use the tangent function to compress everything to within the interval 0 to pi, pi being Nyquist rate. Okay. So it's a kind of a nice figure to refer to. Yeah. So note that the omega, this is what I was talking about, the infinite frequency range in big omega now is mapped to a finite range of 0 to pi. Okay. And that's the power, the beauty of bilinear transformation. It does that for us. Okay. So far so good. This figure. Do you know how to read it? Look at this sideway, and then just for this frequency, for example, omega, the beginning point of a stop band right here. Now refer to this curve. Then back here, there is a small omega s. Okay, using this relation. We will understand that tangent can map tangents is in this range, 0 to pi. Okay? This relation. Okay. Of course, we've been missing a lot of details, but sort of to give you an overview of how IR filter, how we design an IR filter, using low-pass filter as an example. We're using low-pass as an example. Okay. So now, the second kind of filter, FIR, finite impulse response. How do we do that? Now the key idea, forget about analog for prototype. We were done with IR. Okay, so but not to FIR. The idea starts from looking at the ideal filter. Okay, look at the ideal filter. So what do we mean ideal low-pass filter? Ideal low-pass filter, just already in the discrete time, in the realm of discrete time systems, we know small omega is from 0 to pi, for sure. And an ideal filter has constant gain of 1 in the pass band. This is called pass band. And then here, this range is called stop band. The bandwidth within which the gain is 0, to stop that all of those frequencies. Stop band to pass the frequency, to stop the frequency. Therefore, the name stop band, pass band. Okay? So an ideal low-pass filter should accept everything equally in the pass band while rejecting everything completely in the stop band. Okay? Gain 1 in the pass band, gain 0 in the stop band. So that's an ideal low-pass filter. Okay? In the frequency domain. So very soon, just in a very similar way, if you perform inverse DTFT, okay? Inverse DTFT, we all know how to do that, right? So Hn equals to, there's a formula, just integrate everything E j omega n, and you just accumulate everything with respect to the frequency, to small omega, right? So we've seen that over and over, right? So if we do that, then the result is G of n. The result is G of n, okay? The result is sort of a discrete time sinc function, if you will. The result, so it's rather, so G here is H. G is H. Let me just use G. If this is the desired response, then, G of omega, okay? So that gives you the ideal low-pass filter, the what? The impulse response of the ideal low-pass filter, right? So we have this relation. So G of n looks like a discrete time version of the sinc function with this envelope. The sinc envelope, and then but it's in discrete time. Okay, maybe something like that. And symmetric when before time 0. Okay. So this is the desired impulse response for ideal low-pass filter, which completely reject anything in the stop band. But when we say ideal, that means it cannot be achieved, right? So there are a few problems with this, okay? This thing cannot be implemented. First of all, it's non-causal. Okay, it's not zero before time, non-zero samples before time zero. So this is non-causal. What's worse, this impulse response extends infinitely on both sides, right? It extends infinitely to the left and infinitely to the right. Infinity to the left, infinity to the right. Okay? So this is something that cannot be implemented. Right, so what should we do? So very naive, remember the word naive, right? 天真的, right? How about that? Let's do it naive. The naive way I will just suggest, hey, how about let's just cut, truncate the ideal response from minus n to n. Just keep the middle part. And then just keep the middle part while setting everything else 0, okay? Ignore whatever beyond this range. Ignore. And keep the middle part, okay? Keep the middle part, and then use it as a sort of approximation, okay? Use this middle part as the impulse response of your FIR filter, okay? So now we have finitely 2n plus 1 samples. That becomes something we know that to use this response for processing a signal, you simply perform convolution, because convolution in time is multiplication in the frequency, right? So that's the idea. A very naive. Just keep the middle part. And congratulations, you have designed something, okay? And congratulations, that's a design. Even though it might not be the best, but it's a design, right? That intuition is actually not too bad, okay? So we will learn how to analyze how good this, is there any concern about this very naive way of just keeping the middle part while ignoring everything else, okay? But now, this becomes finitely many sample is an FIR filter, finite impulse response. This impulse response has a finite length. So it's something that can be implemented. Okay, that's something that which can be implemented. All right. So the idea right here is just let me just summarize what I just said. This is an ideal response. The impulse response, the expression in terms of sinc function in discrete time, is an ideal impulse response for low pass filter with the cutoff frequencies, omega c. Let's say this is the cutoff frequency, omega c, where c, of course, c stands for cutoff, okay? Cutoff frequency here, and then the ideal response is infinitely long, and therefore it cannot be implemented. Therefore, a naive way is just to make a truncation. Keep the middle part. Keep every sample between minus n to plus n while setting everything else. Truncation, okay? Just throw them away. Everything else is thrown away, okay? And congratulations, this already can be called a design, as I'm pretty sure we can call this a design, okay, already. That's our first design, you know? Very simple idea, but it's our first design, It's our first design because it will be our first FR design, because later in class, we'll see how to do better, okay? Turns out that the better way, better consideration is to multiply this further with something called a window function, okay? Just keeping it in the middle is okay, but it's not the best thing you can do. We recommend that maybe this middle part has to be multiplied by something, okay? Let's shape the middle part by further multiplying all the samples here. We multiply all the samples here, okay? Multiply it, let's consider multiplying it with a window function in this interval, okay? So this window function might be, let's say, another naive. How about just put a straight line? Okay, that's a window function, right? Multiply h sub n of n with w, and then congratulations again, you have another design, Okay, but it's not the best yet. so I mean, design is sometimes there's no absolutely right or wrong answer. If you have an intuition, go for it and see how about the frequency response, right? Which is just the process goes back and forth. You have an idea, you try it out, and you analyze it, right? Then you analyze your system to see if the performance is satisfactory, is satisfying all the specs, right? So the process can go back and forth. But already we have two competing designs, right? One is to just keep the middle part without any shaping. And second is to multiply your middle part, maybe with some sort of window function. Maybe this one, maybe something more elaborated, okay? 也许有更好的, yeah. So that's sort of the first idea of the first general method of designing an FIR filter using the window method, So here we'll be looking at a few commonly used windows. They all have different names: the Hamming window, the Hahn window, Blackman window, Bartlett window, which is the straight line I was talking about. Okay, yeah, sure. You have intuition, go for it. And different sort of windows can be used. And then at this point, maybe before we start jumping into the details of designing IR filter or FIR filter, maybe let's spend some time to talk about what are the general design goals, okay, design goals. And here we use the low-pass filter design as our example. So if we take a look right here, first of all, there is a transition region, okay? You need to create a buffer between pass band and stop band, okay? So first of all, when design low-pass filter, usually we allow the gain to make a transition from 1 to 0. Okay, so that's a very key, important idea. When we design a filter, the performance is not going to be ideal anymore, right? Because ideal cannot be implemented. So every time we apply an idea, we sacrifice on some performance, okay? So one compromise we're making right here is to allow transition. We allow the gain to gradually drop from 1 to 0, okay, between the pass band with the cutoff frequency right here, maybe omega p, p stands for pass, right? Pass band, the edge of pass band, the edge of stop band begins later, and in between we have a transition region, a transition band, okay? So that's a sort of a general formulation. We allow transition. It's okay to have transition because we simply cannot avoid making the transition. Right? Transition takes a bandwidth. Okay? Can we agree on that? Transition also takes some bandwidth. Okay? Pass band, transition band, stop band. Okay? First of all, so then usually we'll be looking at several examples. Usually within the pass band, we can tolerate some error. Ideally, we want the gain to be 1. But we can tolerate some ripple, so to speak, ripple, 涟漪. Ripple is when you drop a rock in the lake, the kind of small wavelets that it's making is called ripples. Ripple. So we allow we can tolerate some fluctuations within passband. The gain can be in between the upper limit and lower limit. We can allow there's some tolerance, okay? So, and same thing for a stop band, okay? Stop band is just usually the gain would not be completely 0, okay? We can allow a small gain, much lower gain than the passband. If that happens, we are fine. So we can tolerate this, in this example, we can tolerate up to delta. The gain that's the gain we are willing to tolerate in the stop band, okay? So now this entire picture is called a tolerance scheme. It's all about to tolerate. 忍受, 承受, we can tolerate some error, some design, some degree of being not perfect, okay? We can compromise, we can tolerate. So this is called a tolerance scheme. with the edge frequencies as well as the magnitude of the maximum ripple we are about to accept. Okay? So this becomes the specification that I was talking about. We expect the performance to be up to so much deviation that we can tolerate. So this becomes something that is specified, that's given for us to achieve. Okay, tolerance scheme. So within the tolerance scheme, we can ask, ideally we want this ripples to be as small as possible while the transition to be as narrow as possible, right? If the transition becomes narrow and the ripple becomes small, then it becomes more and more more and more ideal. Okay? Did you get that? Yeah. Ideally, we want the transition to be narrow and the ripples to be small. We want the delta to be small, delta. We want these delta values to be small, while the transition width should be kept as narrow as possible. So we make the transition from 1 to 0 as quickly as possible. Okay? So, but as you might expect, these two goals turn out to be conflicting goals. Sometimes when we want to suppress the ripples, then so you need to make the transition width wider, or the opposite, right? If you want the transition to be really narrow, then you need to tolerate more ripples. So that's sort of the general trend. I mean, transition and ripples are two conflicting design goals. Okay, we'll cover that. Any comment on this? Okay. Yeah, we will design some homework. Okay. The next homework, you have a computer part, so you will be using MATLAB to design an IIR filter. So you'll play with the different parameters to see how the transition width changes while the ripples and the tolerance scheme is satisfied. We design homework like that. Yeah. Okay, so now a few words to say about this second way of designing an FIR filter. Okay? The first way begins with ideal response, and then we shape the response by applying a window method. That's the first method for FIR. The second method for FIR is called optimal design. 最佳的 optimal design. In what sense? Turns out that when designing a filter of length L, okay, so let's say you have a causal filter of length L. So the L plus 1 samples can be denoted as H0, simply H1, all the way up to H of L, right? L plus 1 samples. So now, optimal design, when we have a vector of H0 to HL. So this is a vector that belongs to the space of L plus 1 samples. Okay? So within this space of all possible filters, within all possible filters, if you take the Fourier transform, you get H, right? H of Ej omega. Okay? H of Ej omega. And let's say H of Ej omega and the desired response is G of omega. Okay? So the difference is your design error, right? So if you take the absolute value, that gives you the design error. Compare your frequency response with the desired frequency response. Desired, for example, the low-pass filter. Take the difference, and then consider the max. Consider where this error reaches its maximum. And that's something to be minimized. You see what I'm saying? Yeah. Consider the maximum error, and you want to minimize the maximum error. That's the idea of optimal filter design. Okay? So we are going to, I need to erase this. Because I need to use some space. Let me erase the window method. The optimal method I'll repeat it. The Fourier transform of small h is, of course, denoted as big H. That's your design, right? And then your design will be not ideal, right? So in general, they're different. And the error, taking the absolute value, is something that we can evaluate within from 0 to Nyquist, right? So there must be a frequency where this error is maximum, right? And this error, maximum error, is to be minimized, okay? So need to now becomes that we need to search all possible H vector within the L+1 space, dimension space. Find the vector which minimizes the maximum error. And then your design is the argument which minimizes the maximum error. The argument, I actually put wrong way. Yeah. The argument within all possible field systems of this many samples, okay? It's in a vector space. And in this high dimensional space, find the one impulse response which minimizes the maximum error, right? That's the formulation. This problem is formulated as a min-max problem, okay? Finding an argument that minimizes the maximum approximation error. So, and this is the error I was talking about, For example, okay? So that's sort of kind of a spirit for optimal design of a FIR filter. You have finitely, you assume that your vector, your impulse response is finite, right? Then search within this L+1 dimensional space. Search in that space in any possible way, such that that maximum error is minimized, okay? So it's an optimization problem for sure, a minimax problem, a minimax problem. Minimizing the maximum of something, okay? So we'll cover that near lecture number 9, okay? It turns out that a few things I want to mention, we can just listen. The optimization method turns out it requires very different kind of math, which involves the Chebyshev polynomial. So anyway, so this is just a preview. Okay, this is a preview. Hopefully, this encourages us to study further. Okay, pique our interest. Hopefully, this piques your interest. Pique interest. Hopefully, this piques our interest. Pique, the verb. 培养胃口了啊。Pique your appetite. 加一些香料，pique your interest. All right, so that much about an overview. Maybe let's take a 5-minute break, and we come back on 17:20. Okay, 5:20, 20 minutes past 5 o'clock. Yeah, let's take a break. Yeah.那就是说，因为你知道，如果不写这个 expression 告诉我那个 error 有多大，最小的 error 有多大，那能够实现到最小的那组 filter 叫做 the argument which minimizes， 也是把什么时候 h 送进去这里面的时候，会让这个 minimize， 所以那个 h 叫做这个 h， 这个意思。对，the argument。 Okay, so can we resume? 可以重新开始吗？啊 Can we resume? Okay, so now we are in this next lecture on a filter that's IIR, and we have the name of that filter is called Butterworth. Okay, it's pretty commonly used. Yeah. Butterworth IIR filter. So we first talk about the definition of the prototype. Okay, the prototype will be an analog filter, and then we'll introduce the bilinear transformation as well as in this lecture note. I'm also giving you some intended reading materials on the textbook. Now, all right, so let's take a slow look. Now, what's going on right here? This is the analog Butterworth filter as our prototype, okay? Now here we have an expression for h of s. We have an expression for h of s. Please spend 20 minutes, oh no, 20 seconds, sorry. 20 seconds to look at this expression, right? 20 seconds, take a look. What's going on right here? What's going on? What's going on? On top is just a constant, so that we can ignore that. Yeah. At the bottom, we have a product. Okay, we have a product of n terms, each being s minus something. Okay. Yeah. So here, if we just draw the s-plane, so I recommend let's draw the s-plane with real part and imaginary part. This is the s-plane, Laplace s-domain. Okay, and h of s. Now, at the bottom here, we have a product of s minus something. Everything here is a complex number, right? Everything here is a pole on the complex plane. And if you note that, please pay attention that here, all the poles are located on the same circle. Did you realize? Now we have a circle on the s-plane with this radius, okay? The radius is denoted as big omega sub c. Okay. So let's try to draw a circle with the radius of, let's say, omega c. There's this circle, okay? And here we are going to put our n different poles on this circle. That's what it means, okay? So now omega c, and there is an angle shift of that. So, and just be careful, pi divided by 2, and there's n, okay? There's k, okay? Right. So basically, we are about to cut the pizza, okay? That's the way I put it, okay? So let's take n equals to 3 as an example, okay? So I've cut it so many times, I know the answer. The answer is that it turns out that we are going to create what? We're going to create, now, k equals to 1, 2, and 3. Okay, if big N is 3, then we are going to create, if I remember correctly, we're going to create a pole right here with, and here, and here. We are going to cut the pizza, and this is going to be 30 degree. This is going to be 60 degree. Same thing. Okay, I'm not cutting this so well now. 60 degree, equally spaced. Okay, 30 degree. So that's for n equals to 3. Actually, 3 poles. You see what I mean? That's for n equals to 3. It's pretty straightforward. Just be careful, okay? Just here, pi divided with, maybe let's put in number, okay? When k is 1, what do we have? N is 3, k is 1. So let's double check. For example, the first one, when k is 1, we have omega c being the radius, e to the j, right? Pi divided by 2 minus pi divided by 2n. 2n being 6, right? You're just putting numbers. It's pretty straightforward. And then ej, what? K equals to 1, n equals to 3. Yeah? What do we have? Then what do we have? Here, that's 90 degree, 30, yeah, so this is 60 degree plus this another 60 degree, right? So it's 120. That's right here. Yeah? And then similarly, k equals to 2, omega c, e, j. I believe this is the same thing here. Well, e, j. Now, 3k shows up only right here, right? So this tells us that all the pizza is going to be 60 degree wide, right? The pizza angle should be 60 degree, according to this, right? Pi divided by 3. That's the angle of your pizza. Is that clear? One slice of pizza is 60 degree. So that's k equals to 1, k equals to 2, k equals to 3. We are creating 3 poles on the left-hand side. Equally spaced by 60 degrees. That's n equals to 3, okay? And then, so that's pretty straightforward. Do you want to see another example? N equals to 4 or 5, okay? You can work it out. So, turns out that I'm just giving you one more example. If I remember correctly, now how about n equals to 4, okay? N equals to 4, then here we have the circle of radius omega c. Again, real part of S, imaginary part of S. Okay, so I think you can work it out that we have. Can anybody tell me if n equals 4, then what's your angle of one slice? How big is your pizza? If n equals to 4, then each slice of your pizza is going to be pi divided by 4, right? 45 degrees. So it turns out that we have 1, 2, 3, 4. And here, each one is 45 degree. 45 degree, 45 degree. Now you can verify, okay? If I remember correctly, that's n equals 4. When n equals to 4, this expression creates 4 poles equally spaced on the left half plane of S, on the S plane. Okay, is that clear? So that's pretty straightforward, and there is a constant on top. Okay, so far so good. And so that is to say, when we go back to this example, then we have h of S being there's a constant of omega c. It's not that important with third power cube. And then S minus, so now let's name our poles, okay? How about if we call this pole, first pole P1, this location is P1, this location is P2, this location is P3, right? Meaning that there are 3 poles. So now we have S minus P1, S minus P2, S minus P3, where P1, P2, P3 are 3 complex numbers. Okay, so that's just a definition. That's just a definition, and then we have h of S, some kind of, which represents some kind of an analog system. Okay? So this function becomes our prototype. So this is a starting point. Our prototype is our starting point. So far so good? Starting point is a function defined on the S plane. That's our prototype. But then, before we apply, the next step is to apply bilinear transformation. But before we do that, there's an important property we need to realize. You need to understand, like surprisingly, if this is h of S, turns out that if we evaluate the magnitude response, right? when we say evaluate the magnitude response of this system, that means substitute S equal to J big omega. Okay, that's to evaluate this system function on the imaginary axis by making this substitution. S now equals to J omega. How about we evaluate the system function on the imaginary axis? That gives you the magnitude response. Okay, and put a square right here. It turns out that when you do that, surprisingly, the expression is pretty simple. You see? This is quite complicated, right? It turns out that surprisingly, if you even evaluate the square of its magnitude, right? Turns out that that's easy. And this is the surprising part. Okay? This is the surprising part that we should verify in a moment. Okay? But please just stay with me so far, okay? Hang on tight. Hang on tight. This is the surprising part because this is really complicated looking, right? 看起来很复杂嘛, right? This is complicated, but this is very simple, right? This is so simple, we can just now, we're ready to make a few plots. Yeah, make a few plots. That tells us if that's h of j omega, if h of j omega really taking the square is 1 divided by 1 plus omega, the angular frequency, divided by omega c. Now, omega c has a meaning. Omega c really is the cutoff frequency of our prototype. Why? Because if we take a plot, okay, this really is a magnitude response as a function of omega, right? So it's a low-pass response. Can we see that? Can we agree on that? This is a low-pass frequency response. Because you can apply if omega equals to 0, right? So let's make a sketch. If omega equals to 0, what's the gain? If omega equals to 0, then the gain is 1 divided by 1. The gain is 1, right? And how about if omega equals to omega c? What do we have? If omega equals to omega c, the gain is 1 plus 1 to divide 1 half, right? So omega c, angular frequency omega c, now the gain becomes 1 half. Gain squared becomes 1 half. 1 half. And then also note that, please notice that this magnitude response is monotonically decreasing. 它是一个严格递减的函数。This function, as a function of omega, this function decreases when omega increases, right? Yeah. Obviously, when omega increases, the gain decreases. Okay. And how about if omega approaches infinity? What happens? When omega approaches infinity, of course, the gain approaches 0. Okay. So it's really a prototype which has a low pass, a very nice monotonically decreasing low pass response. So that's the sketch we're going to make. Okay. Very nice property, okay, which comes with a surprise because the prototype has a complex looking, a system function that looks complicated, but nonetheless, is magnitude response has a very simple expression, which obviously is monotonically decreasing, is a low pass filter, okay, and this is it's so important that now we call this filter Butterworth. Okay? We call this filter Butterworth. Now, so we should see maybe today or maybe next week we will make a derivation why this is the case. Okay? This looks complicated. We can show that its magnitude square really is that simple. It's very simple. But let me, at the time I want to jump to the last page by showing you this circuit. This is a hardware implementation of this thing here. Take a look. Input on the left, output on the right. We have 2 inductors, 1 capacitor and one resistor. Okay. I just apply AC input, change the frequency, right? This is something that you can build. You can go to any electronic shop and get 2 inductors, 1 capacitor, and 1 resistor. And seriously, I found this from Wikipedia. Seriously, if you put capacitor equal to 4/3 farad, resistor being 1 ohm, inductor being 2/3 Henry. This is a pretty big capacitor, though. It's a very, very big capacitor. But suppose that you will get a big capacitor with a very small resistor, and then just do some wiring and create an inductor. Theoretically, you get a 3rd order Butterworth filter with cutoff frequency of 1 radian per second. Okay. Of course, changing the parameters you design. Yeah. So that's the prototype that really has been well known. So I want to share with you. This is a plot, a diagram I found from Wikipedia, and which tells us that this Butterworth filter is named after this scientist Stephen Butterworth, 1885 to 1958, in honor of his invention. He was a British engineer and physicist. Okay, so this is something real. This is not just simply an expression, but something real, something that can be implemented, and has been well known since old time. Okay, since maybe the 19th century, early 20th century. 20世纪初, early 20th century. People came up with the idea, brilliant design, which has a monotonically decreasing frequency response like that. Okay, mysteriously. All right. So with that background knowledge, I think today I may try to explain. Or do you want to go through the derivation why this is the case? Do you want to go through today? Okay. It piqued your interest already? Or for you for sure? Yeah. In the front row. Okay. So yeah, we want to show this? You want to show this? Yeah. Or exercise? No exercise. Okay, I'll show it for you. Okay. Okay, let me erase this. And this. So we can start from here. Okay, we start from here. Okay, and the tricky part is now let's consider the product of yeah. Okay, so yeah. Hello. All right. Yeah. Okay, so now the trick is to consider that. Consider the product of HS multiplied by H of minus S. So if H of S is omega, what's that on top? Omega cutoff frequency cube divided by S minus P1, S minus P2, S minus P3, right? So therefore, H of minus S, of course, is minus S minus P1 minus S minus P2 minus S minus P3. And on top, we have the same thing, omega C cube, right? So far, so good? So now, next, if we consider just multiply the two of them, what do we have? We multiply the two of them on top. Now we have omega cutoff frequency to the 6th power. And at the bottom, let's make a plot first. At the bottom, we have, actually, it's probably more convenient if we change the sign, right? Change the sign, probably making the expression a bit easier. Yeah. So plus, 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 plus with minus 1 to the 3rd power. Do that. So now, if we just multiply the first expression with the second expression, now what do we have? We have a minus 1 to the 3rd power. Don't forget that. But then, a product of S minus S J. Okay? Where J now I'm gonna claim that J goes from 1 to 6. Not SJ. Did I say SJ? Yeah. Okay, I left it blank. Yeah. PJ. Yeah. No, but now I claim that J can go from 1 to 6. The idea that we multiply two expressions, now we have 6 poles, right? No 0, but we have 1, 2, 3 poles already, and the 4th one, 5th one, 6th one. 第4个, 第5个, in total we have 6 poles, right? Where P1, P2, P3 is like that, and where P4 is just minus P1, P5 is minus P2, and P6 is minus P3, right? So we have a 6th order polynomial of S with 6 roots being P1, P2, P3, and minus P1, minus P2, minus P3. Can we agree on that? Simply by multiplying the two terms. Okay? So if we draw a picture now, what do we have? Now we have the original 3 poles on the left. That's P1, P2, and P3. We have 3 poles on the left. And the radius is omega c. Okay? But now, P4 is minus P1. So P4 is now becomes on the other side of the circle, right? Now P4, just symmetrically, P1 is here, P4 is probably something like right here. That's P4. And P5 is simply right here on the real axis. And P6 is right here. So does that remind us of something? Now we have a polynomial which has 6 roots, equally spaced on a circle, right? Now we have a full pizza. Now the pizza is completely cut into 6 pieces, okay? We have the full pizza. And symmetrically, they are 60 degree each. The wedge, the angle is 60 degree each, right? And they form the 6 roots of one polynomial. So the question now becomes, what polynomial is this polynomial? What polynomial is this polynomial? I'm sure you have learned this in high school, okay? Which polynomial has 6 roots like that? I claim if this is called, this is what we call A of S, okay? Yeah. If we define this as A of S, then I claim A of S equals to S to the 6th minus omega cutoff to the 6th. Because this polynomial indeed is the one and only polynomial which has exactly these 6 6 roots, right? Equally spaced, a fully cut pizza, perfect pizza of 6 pieces, right? 60 degrees per piece. That's the 6 roots of this polynomial, right? That's the one and only, and the leading coefficient, again, the leading coefficient is 1. That's kind of a detail right there. Yeah? So, therefore, now, h s h minus s equals to a constant divided by S6, so that greatly simplifies our business right here. Okay? So that's kind of an intermediate step we have achieved so far. This expression becomes pretty simple, right? But now the next thing here, let's evaluate both sides of the equation by at s equals to j big omega. Okay? So next, let s equal to j big omega. Yeah, let's do this. And I can probably erase this. I can also erase that. Okay, so now h of j omega, h of minus j omega, that's what we are going to take a look at, right? Evaluating that expression on the right by substituting s equal to big J omega, right? Okay? But before we proceed, note that h of j omega is h of j omega. H of minus j omega is h j omega complex conjugate. Why? Because our system has a real impulse response, because there is such symmetry. Okay? So therefore, h j omega, we have finally the expression that we need on the left. Do you all see that? From here to here, complex conjugate, because the frequency response has this symmetry. The frequency response of any system with real impulse response in the time domain has this symmetry. Okay? And this is because h of t, which is the inverse Fourier transform is real. Right? That's the reason we can simply put a conjugate right here. So far, so good. Yeah. Can you trust me on that? That circuit, right? That circuit has no complex. In the time domain, there's no complex, no imaginary part. That circuit, if you give it a delta impulse and it has created a response, that response is going to be real in time. Okay? So that's why we put a conjugate and therefore absolute square right here on this chain. Okay? But on the right, now we are finally using that, right? So on the right, we have like -1 to the, is that to the third power? And omega c to the 6th power. Now S6 divided by cutoff frequency up to the 6th power. But now we evaluate at S equals to J big omega. That's what we're going to do next. Okay? On the left, we figure out that at the very end, we have our desired thing for evaluation. Okay? That's the beauty of this derivation. On the left, on the right, simply we are going to make this final substitution, and let's do that together. So now, -1 to the third power omega cut off to the sixth power s equals to j omega, right? So j omega to the sixth power minus omega c to the sixth power. So what do we have? Are we really getting there? Are we really getting there? J to the sixth power, let's figure out. So we have minus 1 to the third power, omega cut off to the sixth power, divided by j. What's j to the sixth power? Minus 1, right? So we have minus omega to the sixth power minus omega c sixth power. Now we are getting the correct answer. Did you notice? Do we notice? Do we all notice? Do you all notice? Now minus 1 is plus omega c can divide, so we have 1 on top, 1 plus, wait. Anyway, 1 plus omega divided by omega cut off to the sixth power. What is 6? 6 is 2n. So we get indeed this beautiful result, okay, out of Butterworth prototype. We have shown that, at least for the case of n equal to 3, indeed, the magnitude square is equal to that, and then we are using the relation of a polynomial's roots. If we have 6 roots like that, if we recap, we have 6 roots like that, the only polynomial that has exactly these 6 roots is this polynomial. That's the key step. That's the key step. Okay? So, so that's a derivation of Butterworth filter, the prototype, and the magnitude response square. Okay, so that's the tough part, okay? Here I have an exercise, all right? So make a sketch of equation number 2. Equation number 2 is, what is expression number 2? Equation number 2, monotonically decreasing magnitude response, which I just erased. But now let's work on an exercise. I think my exercise is, what is the effect of increasing n? Okay? Because very soon we'll realize n is the order of your filter. Okay? N is a design parameter. Okay? So shall we now take a look at what will happen when we increase n? Okay? What will happen increase n? Does the filter performance get better? Right? Does it get better? Do we get a better filter by increasing n? Okay? So make a sketch of that magnitude square response, and let's observe how that response varies with n. And in particular, we should observe how fast does the magnitude, I say, roll off as omega increases. How fast do we make the transition from 1 to 0 when n increases? Anybody want to guess? When n increases, do we have a sharper transition or do we have a slower transition? Sharper. Anybody slower? Why sharper? Why do you think it is sharper? Because you can simply do it. Does it make sense? Is it making sense? The answer is sharper. So let's take a plot. It's not hard. Okay, so the expression is . pretty straightforward. So H now, the magnitude square has this monotonically decreasing expression 1 plus omega divided by omega c to n, right? So we have shown that there are a few anchoring points. DC gain equals to 1, cutoff frequency, corner frequency gain square equals to 1 over 1/2, and then it approaches 0 as omega approaches infinity, right? So one plot could be like that. But when we increase n, you guys are right. When we increase n, that means the decay is faster, right? First of all, when we increase n, that means when omega increases, this decay, this roll off, what I say, roll off. How fast does the magnitude roll off? Okay, that's a technical term. Roll off 就是说那个频率衰减有多快啊 ？How fast does the magnitude response attenuates? We call roll off. Roll off. So when n increases, this rate of rolling off becomes faster. So that means from here it decays faster as n increases. And just at the same time, meanwhile, the gain becomes more flat, more leveled. The passband extends a bit. This becomes more flat, and the quicker transition as n increases. We get a quicker transition. The answer is quicker transition. I tend to break the green ones. And further and so on. Okay, so that's when n versus as when n decreases, we have a more shallow transition and more shallow decay as n decreases. As n increases, that's the idea. We have a more flat and a rapid transition as n increases. Okay, and the corner frequency is always this. This is the corner frequency, at which the gain is 1/2. Gain magnitude square is 1/2. That's an anchoring point. 不变的一个点, an anchoring point. Okay, now so that's a rather a sort of to summarize, okay? To summarize, really, so today we have shown that counterintuitively, with the prototype which looks complicated, the system function looks complicated to the third power, but then we can show that its magnitude square has a rather simple expression, and we honor the physicist and engineer, British engineer and physicist Butterworth, who was born in the 19th century, and who lived all the way to, wait, is it 1958, right? Did I say 1958? 2 years after this university is established at Hsinchu. Hey. That's the year he died. Happy birthday, NTHU. Okay, I guess that will be it. So next week when we come back, we will introduce. Now this is just a prototype. We haven't talked about how to make it digital. Next week we do that. Okay, next week we will do the transformation. Okay, so class dismissed and have a nice weekend. Thanks for being here.